Let us discuss about the circuit stability. The op-amps are rarely used in open loop configuration. Most of the times, these operational amplifiers are used in closed loop configurations only. Due to its use in closed loop configuration, it is necessary to study the effect of feedback on the circuit stability. So, when we are using the operational amplifier in a closed loop configuration, so we have to know about what is the effect of feedback on the circuit stability, how stable our circuit is when we apply the feedback. Then see a non-inverting amplifier with a resistive feedback. Let us see one non-inverting amplifier. So because the VIN supply has been given to the non-inverting terminal of our op-amp, this amplifier is called as a non-inverting amplifier. So this is the equivalent black diagram for the non-inverting type amplifier including the feedback. Here the feedback has been done by the resistor RF. So VIN is the input voltage and V0 is the output voltage, and the operational amplifier block has been represented as AOL of F, and the feedback section has been represented with the beta or B, and it is a summing section. So at the summing section, this input signal and the feedback signal will get added. If it is a negative feedback, then it will get subtracted. If it is a positive feedback, then it will get added. Okay. So here the minus sign indicates that it is a negative feedback. Therefore, the differential voltage VD is equal to the subtraction of the VIN and the VF feedback signal. Okay. So let us see the forward block and feedback block. So see here the forward block in the sense, so in the forward direction Vi into V0, okay, Vi into V0 through amplifier which is called as forward block. The feedback section will contains, this feedback circuit will contains the two blocks. What are they? Forward block and feedback block. So the forward block in the sense the amplifier section, so which is the forward flow of the input to the output Vi into amplifier and amplifier to the output, which is called as forward section. In the feedback section, from the output to the feedback section and the feedback section to the summer section or summing amplifier. Okay, so this is called as reverse or feedback block, forward block and feedback block. Okay, see, as the feedback block uses only resistive elements and hence its transfer function beta is independent of the frequency. You can see the resistor RF is used as a feedback element, so which cannot vary with the frequencies, which is independent of the frequencies, so that we can say the feedback section beta is independent of the frequency. Let us see the AOL of F is equal to V0 by VD. AOL in the sense open loop gain of the operational amplifier. F means with respect to the frequency, which is V0 divided by VD, output voltage divided by the differential input voltage for the open loop op-amp VD, which is equation number 1, where AOL VD is the open loop voltage gain and the closed loop voltage gain AF is equal to V0 by VIN. For the closed loop, V0 is the output voltage and the input voltage is the VIN, which is equal to AOL by 1 plus AOL beta. We have already derived this equation. A by 1 plus A beta is the standard equation. Here AOL by 1 plus AOL into beta or B, where AF is the closed loop gain and beta is the gain of the feedback network. The stability of the circuit is depends upon the behavior of the roots of the characteristics equation 1 plus AOL beta, which is equal to 0. The characteristics equation 1 plus AOL beta. So depending on that, our circuit stability will be depends. Okay, to determining the stability of the circuit, which means that deciding how close the circuit is to the conditions of sustained oscillations. So actually our op-amp has been designed to work like an amplifier. so it has to amplify the signals, and we are using the feedback, okay, the feedback in order to control the gain of the amplifier section. In any case, if our amplifier satisfies the Barkhasan conditions, the Barkhasan conditions has been satisfied by our amplifier, therefore our amplifier will act like an oscillator instead of the amplifier. The Barkhasan conditions we already seen in electronic circuit analysis subject, which is A beta is equal to 1. Okay, so if a into beta, a is the gain of the amplifier section and the beta is the gain of the feedback section. If those two multiplication is equal to the 1, then the Barkhasan first condition has been satisfied, and the second condition, the phase shift around the entire loop is 0 degrees or 360 degrees. If these two conditions has been satisfied, then our circuit will works like a oscillator. So here, if we are calculating the stability in the sense how close our circuit is to start the oscillations. So if our amplifier is very near to the oscillating section, which means it is going to satisfy the Barkhasan conditions, then our circuit will say less stability. Okay, if it is far from the satisfaction of Barkhasan condition, then definitely it is a stable circuit or stable amplifier section. Okay, the system is said to be stable if its output reaches a fixed value with a finite time, and also we can say the system is said to be stable if its output reaches to the fixed value in within a finite time. Okay, then our system is a stable system. The critical values of open loop are 0 decibels and minus 180 degrees. So these two values are very important, 0 decibels and minus 180. So because these two are very important, so this will gives us the stability of the circuit, so that our circuit will start the oscillations at these critical points. So this can be explained using some phenomena, the gain margin GM. So GM is equal to minus 20 log AOL into beta. So here we are calculating the loop gain AOL into beta, and we are taking the decibels, so which is minus 20 log AOL into beta, which is in decibels. And one more phenomena, phase margin, the margin of the phase. The phase margin is 180 degrees plus angle of AOL of F into beta. So these two are very important equation in order to know our circuit stability, gain margin and phase margin. The gain margin is expressed in terms of the decibels and the phase margin is represented in terms of the degree. Also, if these values, see, if the GM is positive, that is AOL of beta is negative, then the system is stable. Suppose if you say AOL of F into beta is a negative value, then definitely the GM will be the positive. Okay, then our system is a stable one, no problem. The negative values of gain margin and phase margin indicates the instability of the system. If these values are negative, then definitely our system is unstable, becomes unstable. How the phase margin will becomes negative? If the angle of AOL beta is greater than minus 180 degrees, then definitely it will be a unstable system. How the GM will becomes negative? If AOL of beta is a positive value, if AOL of beta is a positive value, then our GM will be a negative value. So AOL of beta must be a negative value and the phase margin must be a negative value. So if those two are negative values, our system is a unstable system. If the GM and PM both are positive values, then we can say our system is a stable system. Okay, let us see the frequency compensation. In order to make Suppose in our system has some differences like this, okay, so definitely we have to compensate it. Okay, if any problem related to the frequency of operation has been occurred in our operational amplifier, then definitely those frequency problem has to compensate. So in order to do that, we have some frequency compensation techniques. See, what is frequency compensation? The op-amp circuit with a single break or corner frequency is inherently stable. So we have already seen one break frequency or one corner frequency operational amplifier. Therefore, those type of operational amplifiers are definitely stable circuits. If the frequency compensation technique is used, which means that if any operational amplifier has more than one corner frequency, that is a unstable, that leads to unstable system. So that's why the frequency compensation technique is used to get the large bandwidth with lower closed loop gain. So in order to make our bandwidth as large as possible, we are going to use the techniques called frequency compensation techniques. Okay, and to alter the response as per the requirement, these frequency compensation techniques are also used to get the required output. Whatever the gain we have, we want that we can easily achieve. Okay, and there are two compensation techniques we have. One is external compensation and another one is the internal compensation. Externally, we are going to add some circuit to our operational amplifier, then that is called as external compensation. And the second one is the internal compensation. Within the IC itself, we have some compensation techniques that we will see. So why we are going for the frequency compensation? In order to get the large bandwidth with a lower closed loop gain and to alter the response as per the requirement. So in order to achieve this, we are going for the frequency compensation techniques. So let us see the first frequency compensation techniques, which is external frequency compensation. The external frequency compensation has been again divided into two methods. One is the dominant pole method, another one is the pole zero compensation method. Okay, these two methods are, one is the dominant pole compensation method and the second one is the pole zero compensation method. Let us see the dominant pole compensation method. Let us see an amplifier with three break frequencies and with the loop gain is A. The loop gain is A, which is given as AOL by 1 plus J into F by F1 into 1 plus J into F by F2 into 1 plus J into F by F3, where F1, F2, F3 are the three break frequencies or corner frequency of the operational amplifier. See, we are going to add one compensation network to our output of our op-amp. So this is our operational amplifier output V0 dash. So this V0 dash has been given to one RC network, which is also called as the compensation network. Okay, after this compensation network, our output will be the V0. So just remember V0 dash and V0 here. So we have to calculate what is the values of R and C also. So dominant pole is introduced by adding a compensating network, which is RC network. By adding just RC network, that is called as the dominant pole compensation. The dominant pole means the pole with magnitude much smaller than the existing poles. The dominant pole means that the pole with magnitude much smaller than the existing poles. The break frequency of compensation network is smallest compared to the existing break frequency. The break frequency of the compensation network is smaller when compared with the existing break frequency. So existing break frequency which is less than that, okay, when we use this compensation, before that original break frequency occurs, the gain will start rolling off. Let us see, the transfer function of the compensating network can be obtained as, see, A1 is the transfer function of the compensation network, which is V0 divided by V0 dash. So for this compensation network, V0 is the output voltage, V0 dash is the input voltage. Therefore, A1 will be the transfer function of this compensation network. I am talking about only this compensation network. So A1 is equal to V0 divided by V0 dash. By the voltage divider rule applying to the network, the A1 can be written as V0 by V0 dash, which is equal to, so here the output voltage V0 is the voltage across the capacitor C, and this can be written as minus jXC divided by R minus J into XC. Actually, we can directly write the voltage across the capacitor V0, which is equal to V0 dash into minus jXC divided by minus jXC plus R. Like that, we can rearrange the equation in order to get the A1, the transfer function of the compensation network. So this can be further simplified as minus j by 2 pi of C divided by R minus j by 2 pi of C, which is equal to 1 by R divided by minus j by 2 pi of C plus 1. And we are taking, so this was achieved by 1 by minus j will becomes as plus j. Then we can write the above equation. A1 is equal to 1 by 1 plus j 2 pi frc. Okay, let us assume fd as it is the dominant pole compensation. So fd is the dominant frequency, which is equal to 1 by 2 pi rc. In this equation, is 1 by 2 pi rc has been taken as fd. Therefore, this equation will becomes as c. Fd is the break frequency of the compensation network or the dominant frequency. So a1 is equal to 1 by 1 plus j into f by fd. Hence, the compensated transfer function will becomes, so a dash is equal to a into a1. Okay, where a dash is the gain after compensation. So here we have the two transfer functions. A is the gain of this amplifier, a1 is the gain of the compensation network. As these two networks are in series, therefore these gains a and a1 will get multiplied in order to get the total compensated transfer function. A dash is equal to a into a1. If we multiply the both, therefore a dash will becomes AOL into 1 plus j into f by fd into 1 plus j into f by f1. So here if you observe, 1 by 1 plus j into f by fd, this one 1 by 1 plus j into f by fd is the a1 transfer function, and a transfer function we already know AOL by 1 plus j into f by f1 into 1 plus j into f by f2 into 1 plus j into f by f3. Okay, this is the equation. So where f1, f2, f3 are the break frequencies of our op-amp, and fd is the break frequency of the compensating network, or it is also called as dominant frequency, where fd has been chosen such that fd is very much less than f1, less than f2, less than f3. So we have to select the fd which is less than the lower break frequency of our operational amplifier. Okay, so where fd is equal to 1 by 2 pi rc, 1 by 2 pi r and c. So the value of R and C is selected in such a way that the loop gain drops to 0 dB with the slope of minus 20 dB per decade. At that frequency, where the poles of uncompensated system contributes a very small phase shift. So at this frequency, the poles of uncompensated system will contribute a very small phase shift. Let us see the frequency response of dominant pole compensation network. So here on x-axis we have taken the frequency, on y-axis we have taken the loop gain, and it is the frequency response curve of the uncompensated amplifier. This is uncompensated amplifier. The uncompensated amplifier has the different roll-off rate. The roll-off in the sense how fast the gain is getting decreased. See here minus 20 dB per decade in the first, after the first corner frequency. After the second corner frequency, it is decreasing at the rate of minus 40 dB per decade, and after the third corner frequency f3, it is decreasing at the rate of minus 60 dB per decade. But if you use the dominant pole compensation before this F1 itself, the gain will start rolling off. Okay, so because the FT has been chosen like that, actually the bandwidth is this one. Okay, where we got minus 3 dB from the maximum. This is the actual bandwidth. When we use a compensation network at the output, then the bandwidth will get decreases. So within this short frequency range, we are getting minus 3 dB value, so that the bandwidth will get reduces, but the gain will roll off at a constant rate of minus 20 dB per decade. That is our main intention. So in order to get a constant roll off rate, so if you observe, the uncompensated network will have the different roll off rates. But here, if you use a compensation network, the gain will roll off at a constant rate of minus 20 dB per decade. This is about the dominant pole compensation network. Let us see the advantages of dominant pole compensation. So as the noise frequency components are outside the smaller bandwidth, the noise immunity of the system improves. So whatever the noise sources and components are outside of our bandwidth, so that's why our noise immunity is more. Our system has more noise immunity. And the next advantage is adjusting the value of Ft so that adequate phase margin and the stability of the system is assured. So we can easily adjust the value of the Ft, our pole compensation, the Fd frequency or break frequency, so that we can achieve the phase margin and stability of the system. So the Ft can be varied. We already know Fd is equal to 1 by 2 pi Rc. By just varying the value of R or C value, then we can achieve the required stability and required bandwidth too. So the disadvantage in this system, if you see, the bandwidth reduces drastically. If you use this compensation techniques, then the bandwidth reduces drastically. So we have already seen this in this diagram, the frequency response diagram. The bandwidth without compensation is this much large, and bandwidth with compensation is very small. Okay, so if the bandwidth is not a main requirement in our system, then we can go for this compensation system.